Okay, yeah, let's start. So welcome everybody. Today we are glad to have as a speaker Professor Francisco in this second talk of our seminar series. Francisco received his PhD in electrical and computer engineering from Oregon State University in June 2000. And currently he's a professor in the computer science department of the Advanced Research Center at Mexico City, which he joined in May 2002. Francisco is the co-author of more than 50 technical papers and several book chapters, and he's also one of the co-founders of Latin Crypt, which is the main conference of cryptography in Latin America. His main areas of expertise are crypto, computer arithmetic, and information security. And today he's going to talk about isogeny-based cryptography with a focus on key exchange protocols. Before starting, I would like to remember to the audience that we have a Q&A chat where you can write your questions there to the speaker. I will try to forward them during the talk so we can have some interaction during the presentation. And yeah, Francisco, please, the stage is yours.
Thank you very much, Santos. I would like to start by thanking you for inviting me to give this talk to Dr. Santos del Pozo and Dr. Mark Manzano. It is my pleasure to be here and to talk about this exciting field, which is isogeny-based cryptography. So today we will present a tale of two isogeny-based protocols. As you will see, the literature is really rich in the years that we have been working on this field. And I will try to focus myself on key exchange isogeny-based protocols only, although as I will mention later, there are many other developments going on. So let's start. So some motivation, isogeny-based crypto, when it was born? Well, it was proposed first by Cobain in 1997. Although his results were published until 2006. Why? Well, it's a long story, but to make it short, he submitted a paper in crypto and was not accepted as far as I understand. So he presented his results in the ePrint archive, IACR ePrint archive in 2006. Independently at that time, these two Russian researchers, Rostovtsev and Stolbunov, presented this also similar ideas in that same year in 2006. So now the first isogeny-based protocol is known by the CRS protocol, following the initials of these three researchers. Also in 2006, Charles Leuter and Goren presented the hardness of the pathfinding problem to create hash functions. That hash function was not especially fast, but the thing is that it was based on the problem of isogeny graph, and also the importance of the supersingular elliptic curves were already understood by the authors. And besides key exchange protocols over the years, there have been many isogeny-based cryptographic constructions. We can mention, for instance, digital signatures, that now is a fashion, also verifiable delay functions, which is another important topic, oblivious pseudorandom functions, and many more. But in this talk, we will only talk about isogeny-based key exchange protocols, specifically on that subject. And we have two main families. The first family is the supersingular isogeny Diffie-Hellman key exchange, best known as SIDH. SIDH was proposed in 2011 by Zhao and Defeo in PQC, and it got immediate traction because it was an interesting idea. Later on, it was transformed and the Supersingular Isogenic Encapsulation Protocol, SIDH. So sometimes you would hear more about SIDH rather than SIDH, because SIDH is one of the candidates in the NIST post-quantum cryptographic standardization project effort. Actually, it made it to the third round as one alternative candidate. People refer mostly to SIDH protocol, but in this talk, we will be talking mostly about SIDH, which has the most important ideas that I would like to discuss in this presentation today. Both SIDH and SIDH, they operate on supersingular elliptic curves. They are defined over FP squared, where P is a large prime number of this form. Maybe you don't see this exponent, but it's 2 to the EA, A of Alice, and 3 to the EB, B of Bob minus 1. You will see why I'm saying that Alice and Bob in a moment. The time coasts of SIDH and SIDH are dominated by the computation of large smooth degree isogenies, and we will discuss a bit about this and scalar multiplications. And this is one branch of key exchange protocols, isogeny-based key exchange protocols. The other interesting branch that was born only in 2018, 3 years ago, is CSIDH. That's the way to pronounce it, because it was conceived in Tenerife. And the authors, they were saying, well, if we are close to the sea, let's call it E and SIDH and pronounce it that way. So this is pronounced CSIDH and was proposed. It was published in Asia Crypto 2018 by Kestrick, Lange, Martinoli, and Pani and Renz. This is a remarkable protocol. Because of many reasons, but one of them is that it allows an efficient key validation procedure. And this is interesting because it allows us to have to support static dynamic and static non-interactive, and I emphasize that it's non-interactive key exchange protocols. So this is the closest that we have out there that to the original Diffie-Hellman protocol. Considering all the NIST candidates, considering SIDH, this is the one that most mimic the Diffie-Hellman protocol, the CSIDH protocol. CSIDH operates over supersingular elliptic curves, defined this time over FP, not over the quadratic extension, but directly over FP, where the P has now this form. Is usually is a cofactor, and in the original proposal was 4, and then a product of LIs. These LIs are small primes, as we will see, and this n can have a value of some tens or cents of hundreds of primes. For instance, in the original proposal, n was equal to 74. So the first 73 primes and some other prime there for 187, so that this whole thing is also a prime FP. In the case of CSIDH, again, we will see that the computation of this protocol is dominated by the computation of many odd prime degree isogenies that we must compute, and by scalar multiplications. And in order to have a good balance between these two operations, we will have to have some strategies that are called optimal strategies, and we will also briefly discuss them later on. So SIDH SIDH on one side and CSIDH have been studied and implemented in an impressive number of recent publications. However, until today, very few of these works have been published trying to exploit the parallel opportunities that SIDH and SIDH protocols can offer. These are more parallelizable, in my opinion, than CSIDH. So we will discuss also a little bit about how one can parallelize SIDH. So some math background before starting with these protocols. We will be referring here to elliptic curves given in the Montgomery model. So the curves will look like shown in this equation, where a squared should be different than 4, b should be different than 0, so that this elliptic curve is valid in the Montgomery model. By this notation, we denote the set of all finite points that form an abelian group that satisfy the equation of the elliptic curve equation. And one important concept that we use often here in isogeny-based crypto is the J invariant of an elliptic curve. In the case of the Montgomery model, this J invariant is defined as shown in this equation. And you can think about this as a fingerprint for elliptic curves because it divides the elliptic curves in classes. All the elliptic curves that share the same J invariant, they are isomorphic among them. So this is a good way of classifying elliptic curves, and it's going to be exploited in our protocols that we are going to discuss later on. So this is how they look, our elliptic curves in Montgomery form. There are several tricks that we are not going to have the time to discuss, but for instance, there was a nice trick introduced by Costello, Longa, and Nari in what was declared the best paper award in Crypto 2016 for implementing SIDH protocol, and they proposed to use a projectivized way to imagine the constant of the elliptic curve. Because one remarkable thing about these elliptic curves is that they are agnostic with respect to the constant B. So basically you can focus on the constant A. And the proposal by Costello, Long, and Enrique was to projectivize also this constant of this elliptic curve so that you could have more efficient arithmetic for the elliptic curves. The advantages of working with Montgomery curves, probably you are thinking about that if you are familiar with elliptic curves. The main advantage is that you can work in X-only arithmetic. And this is going to be crucial for having a nice efficiency in our protocols. Although you will see that they are not that fast compared to other NIST kind of candidates, but still, it is important to have X-only arithmetic. And then that implies also that we are going to use Montgomery ladders, most probably because they are it's the Montgomery model advantage. And we will find efficient formulas for computing isogenies in Montgomery curves. For instance, Costello and Hsiel proposed some efficient formulas in Asia 2017. So these are the curves that we are going to be working. As usual, we have the scalar multiplication defined in elliptic curves, which is adding the point P with itself K minus 1 times. We have that the minimum integer such that P added with itself n times is equal to 0. This M is called the order of the point P. And the subgroup generated by P, meaning all the multiples of P, it will be denoted like this, using this notation. This is the subgroup generated by P. And by M torsion subgroup, we mean we are going to use this notation, E square brackets M, and meaning that it's the collection of all the points such that the scalar multiplication of that of any point by M is equal to the identity. So, and we will use a lot this notation, the M torsion subgroup. Another definition, talking about elliptic curves, we will distinguish two main classes, elliptic curves that are supersingular, which are defined like those elliptic curves whose number of points that live in E of FQ is equal to 1 mod P. That means that the Frobenius trace is equal to 0. If you have this condition satisfied, that means that the number of elements of E in FP is going to be P plus 1. You can always know what is the order of the elliptic curve, and then it's called supersingular. Otherwise, if this equation is not satisfied, then you say that the elliptic curve is ordinary. And with these definitions, we can move to define what an isogeny is. It's nothing but a map between elliptic curves. So you have a domain, elliptic curve, and the image elliptic curve E prime. It's a non-trivial homomorphism between elliptic curves. We will define it that way, and they should satisfy these equations that you should expect that the addition of 2 points evaluated in the isogeny should be equal to the isogeny evaluated individually, the addition of that in each of the two points P and Q. Also, you should expect that the identity is mapped to the identity, so that if I apply the isogeny in the identity in the domain curve E, I should arrive to the identity in E prime. These two properties, we are going to exploit them also. Any isogeny in this talk will have a kernel, meaning all the points that live in E, such that when I evaluate those points with my isogeny, takes me to the identity in E prime. And these points are the kernel of the elliptic curve. And for this talk, we will say that the degree of an isogeny is always equal to the cardinality of this group. So we say that E and E prime are two elliptic curves defined over FQ, and if there exists an isogeny between them, then we say that E and E prime are isogenous of certain degree. That isogeny should be of certain degree given by the size of this set K. There are isogenies of degree 1, and in that case, if E and E prime are isogenous of degree 1, we will see that the J invariant of E is equal to the J invariant of E prime, and we say then that E and E prime are isomorphic. And sometimes you can write this property as shown here at the end of this slide. There is a famous accelerator theorem by Tate that says that two elliptic curves can be isogenous between them, or even only if the number of points in both elliptic curves over FQ are the same, as shown in this equation. And if two elliptic curves E and E prime are isogenous, there is only one way that this can happen. Either both of them are supersingular, or both of them are ordinary elliptic curves. Now imagine that you have an elliptic curve and there is a point P in that elliptic curve of order L. So you can try to find then an isogeny to E that we will call that image elliptic curve E prime with an isogeny of degree precisely L. And we call the isogeny computation, sometimes also called isogeny construction, to finding this map phi, such that the kernel of phi is the point P of order L. And then we will use this notation. We will say that E prime is equal to E divided over the subgroup of P, where P is the kernel of this elliptic curve, and where P has order L, and therefore the isogeny also has order L. And this will be called isogeny construction. And finally, another second very important operation that we require in isogeny cryptography is the isogeny evaluation of a point. So imagine that you have a point Q that lives in the domain curve E of FQ, and this point Q is not in the kernel, it's not part of the subgroup of P. Then you may want to try to find the image of the point Q evaluated in this isogeny. And this image is the image of the point Q on E prime, and this is another isogeny arithmetic problem, let's call it like that. Usually, the way that we used to solve this was using Velou formulas, and we were using Velou formulas for the last 50 years. When you try to implement Velou formulas, the best way to do it is by defining 3 different building blocks. One is called KPS, and this is going to try to find all the x coordinates of the multiples that live in the subgroup of P. This is symbolizing here in this graph. So you take the x coordinate of your point P of order L, and then you compute KPS will compute for you 2P, 3P, 5P until L minus 1P. So all the points that belong to the subgroup of P, that will be the output of this block KPS, and those x coordinates together with the elliptic curve. Here, when we say the elliptic curve, what we mean is the constant A. probably projectivized constant A of the domain curve. So you take that constant A and the x coordinates of the multiples of P, and we have a second building block called X isog that will compute for you using the Lewis formula the A prime coordinate of the codomain curve E, the image curve E. We also have this building block called X eval, and X eval will take the point that you are trying to find the image that this point Q that lives in E and is not in the kernel, the X coordinate of that point, also the multiples. You feed X eval with this information, and it will give you the image of Q under the isogeny. What are the costs of these building blocks? So if you use traditional VLU, then the cost of KPS is about 3LM. Here M means field multiplications in FP if you are in FQ, let's say, because you can be in the quadratic extension. So it's basically 3L multiplications for KPS. For X isog is L multiplications, and for X eval is 2L multiplications. So in total, about 6L field multiplications is the cost of the new formula. So basically, you are talking about a linear cost in terms of the degree of L. And you can think about L as a prime number, because if it's a composite number, we have a way to basically to compose the isogenies, to compute isogenies when the degree is not a prime. So you think about L as a prime, and this will be the cost. But just recently, Bernstein, DeFeo, Leroux, and Smith presented in ANS 2020 a new approach that it has been adopted like a square root VLU. And square root VLU is remarkably faster. It only uses square root of L field operations, field multiplications, and it really is practical. This is tight approximation, and if you implement it in practice using all the tricks, which are basically baby step, giant step trick in order to have a faster evaluation of the isogenies, then you get this complexity, and this is going to be exciting for some of the protocols that we are going to mention later on in this talk. I said that you should think about L as a prime number if you want to find isogenies of composite numbers. So the best way to compute them is by using a composition of isogenies, using the homomorphic properties of the isogenies. So imagine that, let's say this case, that this is a large, smooth, odd degree isogeny, that you want to compute this isogeny that has degree L raised to the E. E is a positive number and L is a prime number. It could be as small as 2 or 3 or larger, but a prime number. Then the way to compute this isogeny, it would be like computing, in this case, E isogenies, each one of degree L, and you compose all of them so that the final result, this isogeny has degree L of raised to the E. And we will see more on this later in this class. So this was all my math background, just to make sure that we are in the same page. And so let's have a look on the protocols. So first of all, timeline. As we were mentioning, Kuwait had these first ideas discussed in 1996 about what is known now as the CRS scheme. In 2006, finally, his results were published, and also by Rostov and Bogdanov. Then in 2010, something really bad happened, or if you want to see it in the constructive side. Charles, Zhao, and Sukharev, they published a paper where they found exponential attack on the CRS scheme proposed by Rostov and Stoltenberg. So exponential attack using a quantum, assuming that you had a quantum computer, a large-scale quantum computer. So these are seen to be like a big blow against the isogeny-based protocols. But just 1 year after, in 2011, it was proposed SIDH by one of the authors of this attack, David Zhao from the University of Waterloo, and Luca De Feo in 2011. And the trick that they used was to move from ordinary curves to supersingular curves. And that's basically the SIDH protocol that we are going to review in the next slides. There was then a subsequent paper by Luca De Feo, Zhao, and Jérôme Ploux that was published in 2014. And this has very nice ways to compute the composite isogenies that you have in SIDH. And they have this concept of the optimal strategies in this paper. Later, this paper that I already mentioned, Costello, and Eric, they really have several important algorithm tricks that made like 2 times faster the computation of SIDH. Then when the NIST contest started in 2017, variant of SIDH called that has an encapsulation mechanisms called SIDH was proposed for this contest. And this happened in 2017. And then in 2020, what I already mentioned about the square root value. Before that, Costello presented a variant of SIDH that is called BSIDH. BSIDH. So BSIDH, and we will talk about BSIDH in a moment. And then the square root value was presented in ANS 2020, and we had some implementation, practical implementation of this square root value, and we applied it to BSIDH and also CSIDH, as we will see in a moment. So first of all, let's recap about the SIDH framework. We will be working in the quadratic extension of FP, where P is a prime of this form by Alice, and to the rise to the EB. This is the portion of used by both. This F is usually equal to 1. It's a cofactor. And since we are working in supersingular elliptic curve, we have a control of the order of the elliptic curve. In the quadratic extension is P plus 1 square. So in this case, Alice is going to be and just for
Francisco,
yes, go ahead, Mark.
Yeah, sorry to interrupt. In the last slide, we already started losing you a bit. From the sound, could you just go again on this one, just in case for the audience that might have lost some words?
Absolutely. I'm sorry about that. Okay, so what I'm saying is that here we are going to work with a prime of the form P equal to 2 to the EA. And this portion, as we will see, is going to be exploited by Alice, and 3 to the EB, and this portion is going to be exploited by both. And we will be working with supersingular elliptic curves defined over the quadratic extension of FP. And we have a strict control of the order of the elliptic curve, which is going to be P plus 1 square, because this is a supersingular elliptic curve. We will have 2 characters here, Hermione and Harry, and they will take the traditional roles of Alice and Bob. And as I said, Hermione will focus mostly on this part of the prime, and Harry mostly on this part of the prime. This F is a cofactor, usually equal to 1 in practice. And for efficiency reasons, and also for security, we want that these 2 parts of the prime, 2 to the EA and 3 to the EB, they should be more or less balanced. Ideally, they should have the same size and bits, if you will. So this should be balanced so that the effort that Alice and Bob is about the same. We will have to define a basis. And these bases are 2 points, PA and QA, each one of order of torsion 2 to the EA. And they will form all the torsion points in the base curve. The base curve is E0. And a linear combination of these 2 points, PA and QA, will give us all the points that are torsion 2 to the EA. And this will be used by Alice. So these are her 2 base points. And the same analogously for Bob. Bob will have 2 base points, PB and QB, that they are the basis to generate all the points that are 3 to the EB, torsion 3 to the EB. So these are public parameters for Bob, PB and QB, and these are public parameters for Alice, PA and QA. So Alice starts by computing this isogenous curve EA, but before she's doing that, first she needs to come out with a secret, which is this scalar MA. With this secret and using the base points that she has, PA and QA, she finds this secret point KA. And now that she has this secret point KA, she can compute this isogenous curve EA. And this is Alice. And in the case of base points PV and QB, and he will find this isogeny EB. So EB is isogenous to E0, but with degree 3 to the EB, and EA is isogenous. Once that they have found these 2 curves, they will make these 2 curves public by exchanging owls. So Harry will send an owl to Hermione with this information. This is the elliptic curve that I have computed, and these are your 2 points, your 2 base points evaluated in my isogeny that I found. This is what this character is going to do, and the other is going to do the same. So notice that we are giving here some extra information, which are the images of the points, of the base points of Alice or Bob. And so this is a bit different from a traditional Diffie-Hellman protocol that you would ideally expect only to send the curve and nothing more. But in this case, we need to send the curve that the Hermione found, and also the images of the base points of both PB and QB. Once that they have this information, so what Bob does is, or first what Hermione will do is, she will compute the image of her secret in Bob's isogeny using this scalar multiplication that you will be solving using a Montgomery ladder. And then she is able to find a second elliptic curve that we will call EBA, because it is basically the curve of Bob evaluated in this kernel. And Bob will do the same, but with his secret. And we will call the Bob's elliptic curve EAB, because it's going to be the elliptic curve of Alice or Hermione using his kernel K prime B. And just because of the way that this has been constructed, the 2 elliptic curves are isomorphic, meaning that they have the same J invariant. So basically, they will use the J invariant of a hash of the J invariant, if you will, as the shared secret that they have computed using this protocol. If you prefer to see it just using equations, math equations, so this is the way that it looks, the protocol. First, you have the base elliptic curve here, and then this is called the key generation phase, and this is called the share secret phase. This is the second phase. So this is the SIDH protocol. What are the main building blocks that we have? Well, we have to compute scalar multiplications, but they are called 3-point scalar multiplications in the sense that you have a point P plus M times Q, where M is the secret that Alice or Bob have. And to do this, you can use several tricks, but the standard way to do it is using the right to left Montgomery ladder proposed by the floor team in 2018. And this has a cost per step in the ladder of 2 doublings, basically, because it has 1 addition and 1 doubling as any Montgomery ladder, but in Montgomery model, the cost of these 2 guys are about the same. So basically, you say that you have 2 doublings. This cost of computing 4 different scalar multiplications for 3-point scalar ladders, they take maybe 15–17% of the whole computation. The other part of the computation is, and this is mostly, you can think that this is a sequential computation, but we will see that there are ways that you can accelerate this. Yes, the other part of the computation is the isogenous. And to compute the isogenous, we will have isogenous of degree 2 to the EA and 3 to the EB. And the way that we are going to compute it is by using the composition and optimal strategies as defined in the Defao Zhao and Plut paper. And this will take more than 80% of the whole protocol. How can we compute this isogenous? Well, there is this definition of a directed graph that is a right triangular lattice having E times, basically E times point included in columns and in rows. So basically you are giving this point R0 and you are trying to find this point RE minus 1, following several rules that you need to find. So the objective of the game, again, is to compute an isogeny of degree L to the E. And you take the kernel R0, and first you perform scalar multiplications. So you go down until you go to the leaf, and you compute this multiple of R0, that is L raised to the E minus 1. This point will have degree L, and this allows you to move one column to the right by applying isogenous. So the way to move this graph is you go down using scalar multiplications by L, and you go to the right using isogenous of degree L. And so this is the way that we move. The nodes of this graph, they represent points. And, the to the right are evaluations of isogenous of degree L, and the edges going down are multiplications, scalar multiplications by L. So the way to go is interesting because you cannot move to the next column unless you have visited the leaf. So the first move that you need to do in this computation is mandatory to go from R0 all the way until here. Once that you get here, you have the kernel to move one step to the right. And then you can do different strategies. One strategy could be to compute an isogeny of degree L on R0. So you move to this point and then perform scalar multiplications and go all the way down. And you are trying to move to the right until you get to this point. When you get to this point and you are almost done, you just need to compute a final isogeny of degree L. And then the result will be an isogeny of degree L to the E. So this is the interesting way to do it. Here are two naive ways to do it. You can go all the way down, and then you are allowed to move to the right using isogeny of degree L, and then you move all the way down, and you are allowed to move one to the right. And you keep going like this. This is an example of degree L to the 8 computation. And this is dominated by scalar multiplications, which are the blue edges, and they are vertical, and they are mostly sequential. But you can also do it in another way. For instance, you can go all the way until this leaf, and then compute all the isogenies of the points in this column that you should have been stored. You just have stored in a table, so that you can move all these points to the right. And then when you generate this point, you have already the kernel to move to the next column, and then to the next column, and then to the next column, and like that. So if you think about the cost in reds, you have 36 reds and only 8 blues. Also, that means 36 isogenies of degree L and 8 blues. And in this case, it's the other way around. So this has quadratic complexity for the blues and linear complexity for the reds, and the other way around. Something balanced. You can think about better strategies. For instance, I am showing you here in the left a strategy that only uses 20 reds and 11 blues. 11 blues again is scalar multiplications, and 20 isogenies of degree L, or this other strategy. So how can we come out with the best strategy? Well, this was defined in the paper by by Zhao, Plut, and DeFeo, and is you can divide the problem into sub-triangles. So if you are trying to find the best strategy for this triangle, you can divide it in an upper triangle and lower triangle. This of size H, meaning that has H columns and rows, and this has E minus H columns and rows. And you try to find the best partition given the first triangle. And once that you have found that partition, then as you can imagine, what you can do is divide and conquer kind of process. So now you do the same for this subtriangle and the same for the upper subtriangle, and you keep going. And the authors prove that by following this approach, you will have an optimal strategy to solve the problem. Obviously, when you are dividing the big triangle into sub-triangles, you need to find a way to glue the triangles, sort of speak, glue the triangles. And how can we glue them? Well, remember that your point is here, your kernel point is here. So you need to go down to this point using H scalar multiplications by L, and you need to go to the right here using E minus H degree L isogeny evaluations. Now, if you are have followed the discussion before, in order to arrive to this H, I need to compute this leaf because I needed to move to this part. So these are the codes that we have. I don't have time. But using this procedure, you can find a very nice way to balance the number of isogenies, degree L isogenies, and the number of scalar multiplications by L. And basically, you will end up having E over 2 log 2E scalar multiplications and isogeny computations, where E is the size of the first triangle. So this is basically the idea of these optimal strategies. They are optimal. They have been proved to be optimal, but in the sequential single core scenario. If you have a multi-core scenario, then you have to consider extra definitions. For instance, just to give you the flavor of what is the idea, imagine this case. For instance, what we see here in the left is a strategy that takes 20 isogeny evaluations, the reds, and 11 scalar multiplication. So if you think that they are cost the same, then this will cost 31 units. What we have in the right is a better strategy because it only requires 16 reds and 13 blues, which is going to be 29 versus 31. But this is in a single core. If you are in 2 cores, then all these reds can be computed in parallel. So this is more parallelizable. And if you go to 2 cores, the cost of this goes down to 23, and it ties the cost of the one in the right with 23 because it has less reds and therefore less opportunity for parallelization. If you go to 3 cores, then this only costs 22 units, and this will cost 23 units. So this will be more expensive in 3 cores, and in 4 cores, also the one in the left wins. So the other thing that one trick that you can use is that the first column that you are trying to compute in this triangle, you have to compute multiples of your kernel point. And it just happens that the multiples are less costly to compute than the point itself. There is this proposition. I won't have time to discuss it in detail, but basically you can see it in this picture. What one strategy for parallelizing this problem. What you can do is if you happen to have many cores, you can give to one core the task of computing this point RA. Remember that this is going to be done with a Montgomery ladder, RA, and you can give to other cores that you may have the task to compute this point, 2 to the E minus B RA. And this is much easier. It has 2B less doublings than this one. So this task is going to be finished before the first core is computing RA. And so you can use the time that you have to spare to compute maybe small lower triangle, and then gain some time. So that when this lower triangle is ready, also ideally this will be ready, and you can move to the right, which is our objective. So using these ideas, we implemented one of the parameters of SIDH, P751, which is the largest level 5 security for SIDH. And here are some codes. What I just want to show to you, this was implemented in Skylake and using the Slang compiler. And what I want to show you is cannot have big dreams, big expectations of the amount of parallelization that you can get. There are we found many synchronization problems, but still we were able to go down from 19 millions of clock cycles for the first phase of the SIDH for this prime. We could go down as 12, basically 13 million clock cycles, using the trick of parallelization, the scalar multiplications, and trying to come out with the optimal strategies for parallel environments. So what you have here is just trying to parallelize the isogenies, and then here using the trick of parallelizing the scalar multiplications. And what you have here in this column is that the cost of using the sequential optimal strategy that was reported by Zhao, Clut, and Defeo. So you see that the more tricks that you apply, the more that you reduce the cost of this computation, there is some limit. And this is using 8 cores. Ideally, what you can do is, if you have so many cores, what you can do, you have plenty of hardware resources, then you can compute all these multiples in parallel, so that they cost basically the cost of these this point R, and then going to the right, you can go using each one of the cores that you use for the first part, and then this will be the ideal case for trying to accelerate as much as possible this protocol at the cost of a lot of hardware. So this is all the thing that I'm going to say about SIDH. Now I want to go through the class and see what we can find there. And then there is this proposal that I mentioned already by Costello in Asia Crypto 2020. If you remember, the form of the prime was that for SIDH was that P is equal to 2 to the EA times 3 to the EB, where 2 to the EA is for Alice and 3 to the EB is for Bob. But the idea that Costello has exploited here is, why don't we work in both sides of P, but in the way that P plus 1, the factorization of P plus 1 is going to be handled by Alice, and the factorization of P minus 1 should be handled by Bob. So this is why it's called BSIDH. You will have an elliptic curve as before. You will have points, base points for Alice, and they will give you all the torsion points, P plus 1 torsion points that live in this elliptic curve. And you will have another base for Bob, and they will give you these trace 0 points for Bob. So basically, you will have a SIDH protocol as before, but Bob will be working in the Alice will be working in the P plus 1 factorization. So the factors that you will find there involved in the factorization of P minus 1. So maybe you can see it better if you think in a concrete case, because other than that, the protocol is the same as SIDH. So Alice will find her secret, then she will find an elliptic curve, a supersingular curve, that she will communicate to Bob, along with the images of the base points of Bob, as we did in SIDH. And Bob does the same, and the secret, shared secret is going to be the J invariant. What changes is the way that they are using the prime P. So imagine this concrete parameter that we have for this P that has 237 bits. So P plus 1, so M divides P plus 1, and M is going to be given by these numbers that you can see in this row. So Bob needs to compute, sorry, it would be Alice needs to compute all the isogenies that have degree 4, 3, 17, 19, 31, 37, and 53. and using the composition rule that we just studied. In the case of Bob needs to compute all these isogenous of this degree using composition again. So in this case, Bob has much more work than Alice. So this is nice with Mike's protocols that he was studying some years ago about unbalancing protocols for the client and the server. The client could be Alice and the server could be Bob. And this is a big problem. How can you find primes that are smooth in both sides, in p+1 and p-1? And there are nice ways to do this. This is another prime parameter. This has 253 bits. So this is smaller than SIDH. This is nice. And this is the site of M, the site of Alice and site of Bob. And these are the isogenous that Alice must compute. These are the degrees. These are going to be her LIs, and these are Bob's LIs, the ones that I have. So in the very last slide of my presentation, I will talk about this. The way to accelerate these isogenous, since they are large degree, we need to use a square root value. A square root value doesn't work for, or doesn't help for SIDH and SIDH, because SIDH, as we saw, they have only isogenous of degree 2 and 3. So a square root value doesn't help in that case. But for CSIDH, they help a lot. But only with big instances of C-side that we are going to see in a moment. And for B-side, the one that I just mentioned here, it is a game changer to use a square root value that makes B-side not a theoretical protocol, but a practical protocol. We will see it at the end, the very last table of this. Yes?
Sorry, Francis. We have 5 minutes left.
Okay, thank you. So C-side was presented in 2018, and the nice part about C-side is that it's the closest to a real Diffie-Hellman protocol could be. There have been many papers about this. This is the timeline. Maybe if you have the chance, you can check later this presentation for seeing all these developments that have occurred across these 3 years. From 2018 until now, and and then you have optimal strategies, but now defined in the context of C-side. And how does it work, C-side? Well, this is the scheme that we have. In this case, we will be working in FP, supersingular elliptic curves, but not the quadratic extension. And Alice, her secret is going to be a bunch of exponents. N exponents that are going to be in the range from -m to n, the same action. So she will find an isogenous elliptic curve EA that has that is isogenous with E of degree L1 raised to E1, L2 raised to E2, up to Ln raised to the En. So the secrets are the exponents in the case of Alice. And in the case of Bob, also the secrets are the exponents, and he finds this curve EB. Alice gives to Bob EA, Bob gives to Alice his elliptic curve EB. And then Alice operates now in the curve of Bob using the same configuration of small primes and exponents. She finds this isogenous elliptic curve EBA that is going to happen just by the commutativity property of this protocol equal to the elliptic curve found by Bob. The prime that we use in this case has this form, 4 times a bunch of LIs minus 1. For instance, this could be one configuration of the prime. So if you factorize, if you put this 1 on the other side and divide over 4, you will find this product of LIs. And these are the isogenous that Alice and Bob must compute using the exponents that are given by the secret keys that they have. So this is basically the idea. I won't have time to show you the nice properties that they have because we are running out of time. So I will focus on this table to finish my talk. So what you have here is the cost of several isogeny-based protocols. So the SIDH protocol, the one that is an alternative candidate of the third round of the NIST contest, if you want to run a Diffie-Hellman, full Diffie-Hellman protocol, it takes, for the smallest parameter, which is a prime of 434 bits, it takes 22 millions of cycles. The original CSIDH, as proposed in 2018, was a non-constant time implementation that took 4 times 155 millions of cycles. So it is expensive, this CSIDH 512, even though it's a non-constant time protocol. And this happens also for these implementations. The fastest CSIDH that we have at size of 512 bits takes 4, and which happens to be constant time. It takes 4 times. So basically, it takes 1 billion of clock cycles. So it is a slow protocol, the one that we have as a site. The B site that I was mentioning in this talk takes 119 million clock cycles. So it's more expensive than his cousin SIDH, but not that far away. And CSIDH 512 is definitely much more expensive than SIDH and B-SIDH. So this is just to give you an idea of what are the costs in millions of clock cycles. These are Skylake clock cycles of these protocols that we were trying to review more or less in this time frame. So thank you very much for your attention.
Okay, yeah, thank you very much, Francisco. Yeah, it was very interesting talk. Yeah, unfortunately, we ran out of time, and but, yeah, so I don't think we have any questions. So yeah, okay, yeah, we have a question from Emmanuel. So he's asking to have an idea, what are the clock cycles for Diffie-Hellman with classic elliptic curves?
Thank you for the question. It's a nice question. Oh, you are talking about the protocol that is the fastest, is non-quantum resistant. It should be in the 100,000s of clock cycles. So I would say maybe below 200,000 clock cycles for an elliptic curve of security of 128 bits. So the latency of these protocols is considerable. Yeah, maybe a fairer comparison would be with other NIST candidates, like the lattice candidates. They are also much faster than this, like 1 order of magnitude, basically, roughly speaking.
Okay. Yeah, we have another question from Victor Mateu. He says that we keep seeing new schemes based on isogenies, which provide a nice Diffie-Hellman-like interaction. But in each evolution, it grows the cost of the implementation. And he's asking, why is there so much focus on new schemes, but we do not see much on the side of fast implementations?
Well, that's also an interesting question. Well, in my opinion, I didn't have time to go through the timeline for CSIDH, but you will find lots of efforts to try to make it faster for CSIDH. And the same could be said for SIDH and SIDH. But at the same time, people are interested because you would like to have an isogeny-based crypto that is more expressive, right? Not only in key exchange protocols, but having other primitives, cryptographic primitives. So in my opinion, is maybe a question of taste. I would say that both things are important. For instance, now it is very exciting to find maybe PDFs based on isogenes, like the one that was recently proposed by Luca De Feo et al. Or signatures with very short signatures. This is very exciting. But definitely we need to make effort to accelerate them because they are nice but slow. So how can we accelerate them? This is partially what I tried to cover in this talk.
All right. Okay. Javier has a question. Are there isogeny-based signature schemes? And what is your opinion about them?
Yes, they are. There are many. Please don't get the idea that isogenies are only focused on key exchange protocols. There have been several proposals for signatures, and the most recent and well commented is CSIDH. I hope I am pronouncing it correctly because we need to check the pronunciation of these schemes. CSIDH, Best Paper Award in Asia Crypto 2020, if I'm not mistaken. And the nice part of this signature is signature scheme is that is the shortest of any post-quantum signature scheme that has been proposed. This is the nice part. The not so nice side is that they are slow. So yes, we do have signatures based on isogeny.
Okay.
We have time to discuss them.
All right, yeah. And we have a last question from an anonymous attendee. He says, I believe you have a bet with Bernstein about when a quantum computer will happen. Is that true?
No, it's not, that's not the bet. The bet is, we made a bet in Latin Crypt 2017 in La Habana, Cuba with Dan. And the bet was in the ROM session of Latin Crypt. So it's public and you can check it in the internet. It's about, the bet is what is going to happen first, the year 2033, because the bet will last 16 years. The question is if in this period of time, there will arrive a quantum computer able to break RSA 2048. If there is a public result showing that a quantum computer could break RSA 2048, then I would lose the bet with Dan, and it's $1 per bet. If it's not the case, then he will lose the bet, and the winner needs to invite the other to a nice dinner. That's the bet. Still going.
Okay. Yeah, there are a couple of other questions that came in the meantime. Sure. One from Jesus Javier. He said, it's clear that SIDH is faster than CSIDH, but do you think BSIDH could be faster than SIDH?
Yeah, this is a very interesting problem. Yes, BSIDH, the one that we are seeing here in this table at the very last row, you see is like maybe some 4 times more expensive than SIDH, but it has a smaller prime. And this BSIDH can be accelerated because value squared can be accelerated. So there are hopes that this BSIDH will go down, especially if we found, we are able to find better parameters for P. So it's gonna be difficult, I would say, but definitely the gap, the current gap between BSIDH and SIDH or SIDH will reduce, in my opinion, reduce in the next few years, maybe 1 or 2 years, because this moves so fast. And then also we need to find or to define BSIDH, because this is BSIDH, but it would be nice to have BSIDH. But this happens, you know, it will happen in the next year or two, I would say.
Okay, and now the last one from Eduardo. He's asking if have you looked into threshold variants of these isogeny-based primitives? Like, for instance, the paper by DeFeo and Measures at Public Key Crypto 2020? And if so, do you see a way out of the sequential round-robin structure they follow? Because having such sequentially apply, no, because of having to sequentially apply the group action?
No, to be honest, Eduardo, I need to check that paper more carefully. PKC. Yeah, I would need to check it. I only can answer right now the last part of your question about the sequentiality of the group action. In general, we have found that CSIDH is nice because it's commutative, but it's extremely hard to parallelize it. So yeah, I would need to check that paper to have a better answer. But my first gut feeling is that the group action is not amenable for parallelization, not so much, I would say. But of course, I need to check it more carefully. Also, I mentioned in this talk mostly parallelizations in terms of multi-core environments, but vectorization is something that needs to be explored, and maybe their group action can be parallelized.
Okay.
But it's not clear. I don't see it right now.
Yeah, and well, we have a quick one from Mukul. Are there any impossibility results about any crypto primitives from isogeny-based assumptions?
Impossibility results. No one comes to my mind in this moment. I would need to think about it, but no, at this point I would say I don't know of any that comes to my mind. Impossibility result. No, I cannot answer this question. Yeah.
Okay, yeah. So yeah, we are done with the questions. So yeah, I would like to thank you again for the presentation. It was very interesting. So yeah, thank you very much, Francisco. Also, thank you all the attendees for coming today. And yeah, we will keep updating the details of the following talks in the website. Thank you, everybody, and have a nice weekend. Bye-bye.